generally classified based on production rule. This is a taxonomy of grammar. So based on production rule, or based on number of derivation trees, or based on strings, or the language that you generate, or based on the language, you can divide it. This classification is possible. So based on production rule, we are going to see this is called as Chomsky hierarchy. So it's type 0, type 1, type 2, type 3 grammar. So we will see this grammar extensively in second unit. Okay. So this is a classification based on production rules. So you have a production rule of the format alpha tends to beta. Okay. So how this alpha should be and how this beta should be. So the set of rules for how alpha and beta should be in terms of, or with respect to terminals and non-terminals, we'll define a set of rules. So based on alpha and beta, I can classify grammar as 4 types, type 0 to type 3. Okay. And based on derivation trees, now we saw a derivation tree here, right? So based on this derivation tree, I can classify my grammar as ambiguous and unambiguous grammar. Just a very short example for ambiguous or unambiguous grammar. So consider this grammar, okay? That has a production rule, something like E is my starting symbol, let us say. Okay, so this is my production rule. Okay, I can write the same, listen, if in case you don't understand, I can write the same production rule like this. Okay, 3 different production rules also I can write. Okay, so I can write it like this. So remember, I'm going to I'm going to expand it from the left. Okay, we'll see in detail like what is left derivation, what is right derivation. For now, we'll trying to understand the concept of ambiguity. Okay, so E is my starting symbol. So I'll start with E. First, let me decide. I'll choose. So E has many choices over here. Am I right? So I'll try to use this E plus E as the first choice. Plus is not R or something. It's the mathematical symbol, that arithmetic operator plus, let us consider. So I can have E, I can have a plus, I can have a E. Okay. Then I decide to expand this E with E minus E. Okay. Now in the places of E, I'll just substitute A. So what is the final string that I get out of this tree? It is A, then use a plus. Plus is a terminal symbol. I don't have to replace it. Okay. All in capitals are non-terminals. Okay, easy understanding. So A plus A minus is here and a A. So this is a string that I got out of this parse tree. Okay. And for the same thing, in case I choose to, for the same grammar, I can construct a different parse tree. I can choose E minus E. Okay. Then say I'm going to expand this using E plus and a E. Okay. Now I'll substitute all E's with the terminal A. Okay. Now what does this generate? Again, a plus and a, and I get a minus and a. This is a string. Now remember, for the same string A plus A minus A, I have 2 parse trees with me. Am I right? For the same string, if it's a different string, different parse tree, I understand. Obviously, for different strings, different parse tree has to exist. No issues. For the same string A plus A minus A, I have 2 parse strings for parse trees possible. Okay, I have 2 parse tree constructions possible. This is called as ambiguity. Okay, this is called as ambiguity. For this, remember, for the same string, not for the different strings. For the same strings, if there are 2 parse trees possible, then it's called as ambiguous grammar. So we can't use directly, this ambiguous grammar cannot be used for practical application. It has to be reduced to unambiguous grammar. So one string, only one tree should be possible, parse tree should be possible. You cannot build a compiler with ambiguous grammar. So for the same expression that you give, compiler cannot generate multiple parse trees. That's not possible in practical applications. So we try to convert this ambiguous grammar into unambiguous grammar. So that is what we'll see in the next session, is about conversion of ambiguous grammar to unambiguous grammar. Okay, so this is based on the derivation types. Okay, so this is based on the derivation trees. Derivation trees. So same string, multiple parse trees. It is called as ambiguous grammar. Okay, I hope you follow. Any doubts? Please stop me. And the other derivation is in terms of language. So in case the language generated out of the grammar is finite, so it's infinite, it's called as recursive grammar. If it is finite, it is called as non-recursive grammar. The language is finite, it's called as non-recursive. If the language generated is infinite, it's called as recursive grammar. Okay, so these are the basic classifications of grammar. Okay, so unit 2 extensively handles on type 2. But this also we'll see. With type 2, we'll try to see what is ambiguity and we'll try to understand recursive grammar also. Okay. Because type 2 also, all these types can generate both finite languages and infinite languages. Okay, so these are different angles of or different ways in which you can classify grammars. Okay, so Chomsky hierarchy. So type 0. So last class we saw. So type 0 is a universal grammar. So type 0 is the superset. So in that next we have type 1. So then you have a type 2 and then you have a type 3. So all type 3 grammars are type 2, type 1 and type 0 also. Or type 2 grammars are type 1 and 0. All type 1 grammar is the type 0 grammar also. So type 0 is a superset. Okay, we'll see each of one in detail. So remember, this classification is based on production rules. Okay, so this classification is based on production rules. Alpha tends to beta. Okay, so this is purely based on the production rule. So type 0 is called as unrestricted grammar. It has the least restrictions for this production rule. Least restriction. So it's called unrestricted grammar. And type 1 is called context sensitive grammar. Type 2 is context free grammar. And type 3 is a regular grammar. It's the most restrictive is regular grammar. So the restriction increases. So the restrictions increases as we move down. Okay, restriction increases as we move down the hierarchy. Okay, so what is type 0? This is very simple. Okay, just follow the key pointers alone. So they include all, it's a superset. It includes type 0, includes type 1, type 2 and type 3 also. So it is least restricted. Okay, so this is recognized by Turing machine. Machine that accepts the languages generated by this grammar is Turing machine, and the language is recursively enumerable language. Okay, so the language is called recursively enumerable language, and the machine that accepts this is Turing machine. We learn extensively about this when we study Turing machine in 4th unit. Okay, for now, okay, this is understood. We don't know much about recursively enumerable languages or Turing machines. Fine, let us understand, but we know this classification is based on production rule. So we'll concentrate more on the production rule format. See here, so alpha tends to beta is the production rule format. Alpha should be of this format and beta should be of this format. As I told you, V and N are used interchangeably. So V is a non-terminal or a variable and T is a terminal. Okay. So if you see the left-hand side, alpha tends to beta, in the alpha tends to beta, the left-hand side should have at least one variable. That's it. So this is a crux condition of type 0 grammar. No other restrictions. Okay, it should have at least one variable. Okay, so minimum one non-terminal or minimum one variable on the left-hand side of the production. So that is a rule. Okay, so what does this mean? Terminal or non-terminal can occur 0 or more times, then a non-terminal or a variable, then variable or non-terminal or a terminal can occur 0 or more times. So these two are optional and this is mandatory. So definitely the left-hand side should have a single variable, okay? And the right-hand side, optional, completely optional. 0 or more occurrences of terminal and non-terminal symbols. See, epsilon is implicitly part of terminals. Okay, some grammar they define it, some grammar they don't define it explicitly. So epsilon is part of your non-terminal, terminal symbols. Okay, so the condition, the crux condition is minimum one variable to the left-hand side. So that is what we see. I see minimum one non-terminal or a variable in all the examples. Okay, fine. So this is a condition, no other conditions. This is the only condition for type 0. The language that is generated by this grammar is called recursively enumerable language, and the machine that accepts this is called Turing machine. Okay, so we'll see extensively what's the difference between the recursively enumerable language and the regular languages that we saw in Unit 4. As we realize the machines, it will be easy to understand the languages. Okay, for now, remember the condition on production rule. Left-hand side, at least one variable or non-terminal is mandatory in type 0. And that's the least restrictive. Okay, now we move to type 1. So as we saw in this diagram before, all type 1 are type 0 also. So the first condition holds good. A minimum one variable to the left, that holds good still. And apart from that, what is the condition? See here. So alpha and beta both are of the format 3 plus t, 3 or t. Any one should occur at least one or more times. Okay, it was 0 or more time in the previous thing. Now any one should occur one or more time. Okay, and one variable to the left is mandatory because it is type 0 also. Type 1 is type 0, should be a type 0. So that condition is implicit. Okay, apart from that, this is one condition. And length of alpha, number of symbols in alpha, including terminal, non-terminal, all symbols should be less than or equal to the length of beta. So these are two new conditions for type 1. And apart from that, you should add the conditions of type 0 also for the type 1 grammar. Okay, so remember B or T, one or more occurrence, then modulus, that is length of alpha should be less than or equal to length of beta. And other than that, the language generated is called context sensitive language, and it's accepted by linear bound automata. Okay, so it is context sensitive language and it's accepted by linear bound automata, and these are the rules. So it is becoming more strict now compared to type 0. Type 1 is strict. Compared to type 1, type 2 will be strict. We will be seeing type 2 extensively in this unit. Okay, so the rule, again, it is type 0 plus type 1. Okay, and the next rule is like alpha is single NT. Okay, alpha is single non-terminal. You always see a single non-terminal over here. Okay, you see a single non-terminal over here. Okay, so that is mandatory. It should be single. Okay, and the language is generated or context-free languages, and the machine is push-down automata. So this is like a finite automaton along with a memory. Imagine this to be a finite automaton along with a stack or a memory. Okay, so it's a single non-terminal is the additional condition in this. Okay, in type 2. That's the only other restriction. Type 3 regular grammar is the most restrictive grammar. So the language, regular language, automaton is finite automaton. Okay, and it should always be of the form like this, single this side, because type 3 is also type 0 plus type 1 plus type 2. So type 2 said like single variable on the left hand side. So single variable at the left hand side. Variable is also called as non-terminal symbol. So on the left hand side, it should be a single variable. So that should be followed. See, the right hand side should be of this format. Okay, this is called as left linear and this is called as right linear, where your non-terminal symbol is present. Left linear or right linear. You can't write something like this. This is not allowed in type 3. You can't sandwich a terminal between, you can't sandwich a non-terminal between terminals. It should definitely take this format. Okay, either it should be a combination of one non-terminal and a terminal, or a terminal alone is possible. And the non-terminal terminal combination could be either in this order or it could be in this order. So it strictly follows this pattern. So left hand side, one variable. Right hand side, it could be a combination of terminal, non-terminal, but in this format exactly. You can't have sandwiching like this. This is not possible. Okay, so these are the examples. Okay, these are all valid examples. Okay, fine. So these are the 4 types of grammar. So as we saw, these are the languages. So the languages would be, this is a regular language. Okay, so this is a context-free language. This is a context-sensitive language. And this is a recursively enumerable language. So these are the languages accepted by the machines. Okay, so we are going to see type 2 in detail. context-free grammar in detail. I think we had more theory. So we'll just quickly see an informal example. We proved using pumping lemma that this is not a regular language. Okay, so this requires some sort of memory. I have to store n somewhere, right? So I have to store n somewhere. This is a palindrome. When it is represented, this again is a palindrome. So 0 occurs for n time, followed by 1, and then 0 occurs for n time. Okay, either a palindrome, or when you represent it using the binary alphabet 0 and 1, I have a representation of language like this. Now we proved that this is not regular language by using pumping lemma. Okay, so it cannot be defined by a regular grammar, but it is an example of context-free grammar. This is just informal examples. We'll see the formal definition shortly. So this is a set of production rules. For type 2 grammar, what was a condition? A single variable or a non-terminal at the left hand side. Okay, so and one or more occurrence. It should have one or more occurrence of a variable or terminal. That is one. And length of alpha should be less than or equal to length of beta. So since we say one variable at least should be present, so I think this condition will hold good. Okay, so these are the conditions that we derive from type 0, type 1, type 2, etc. So type 2 follows this condition. Okay, now this is the context-free grammar for palindromes. So as you can see, I'll start with a symbol P. You can just write a quick derivation tree and see. I need not use all. I'll use any one rule. Okay, and in P I can substitute a 1 or a 0. Okay, and or I can again expand P with 1, P, and 1, and I can decide to substitute P with 0 or a 1 or an epsilon. Okay, so this is how we draw trees and generate strings. This process is called as derivation. Okay, this process is called as derivation. And derivation could be done either using past trees or using in-place substitution. Okay, and this is example 1 for palindrome. So this is a grammar rules, production rules. Okay, this is not the whole grammar. I've defined the grammar's production rules. So this is a set of production rules. Okay, so similarly, this is a context-free grammar for an expression. So this is for an expression. This is a set of production rules for an expression. Okay, and it follows this alpha tend to be beta. The production rules follows this set of rules. Say a single variable. This is one condition. This is another condition. This is another condition. It follows all these conditions. So it is called as a type 2 grammar. Okay. Fine. The formal definition has nothing special. The same thing. It should follow the conditions for alpha tends to beta. Other than that, it's the same as in the general grammar. Okay, so this is the formal definition of grammar for the palindrome example that we saw in the previous symbol. So grammar for palindrome is set of non-terminals or variables. Okay, set of terminals 0 or 1. A is a set of all these production rules. So all this, in case I name it like P1, P2, P3, P4, and P5. A is a set of all these production rules, P1, P2, P3, P4, and P5. A is a set of all these production rules, and P is a starting symbol. I have to start with P. So starting P, epsilon is an acceptable palindrome. 0, a single 0 is an acceptable palindrome. That is why I have separate rules for epsilon, 0, and 1. Single 1 is also an acceptable palindrome. Okay, then I have patterns. Okay. So this is a formal definition of grammar for palindrome. And applications, so we've seen the informal and formal definition of type 2 grammars. So type 2 grammar, when you think about type 2 grammar, remember push-down automaton only can realize or only can accept the language generated by this grammar. So what is push-down automaton? Just as a shortcut, remember finite automaton with some memory, stack. Okay. Apart from that, what should you understand by just saying type 2 grammar? It has a set of rules. So the classification is based on production rule, and production rule is alpha tends to beta, and alpha and beta should follow the set of rules. What are the rules? Alpha should at least have, alpha should have a single non-terminal or a single variable. Beta could be anything, like V or T occurs one or more times, that is of the format beta. And number of symbols in alpha should be less than or equal to number of symbols in beta. Okay, so it could be, so you should follow the production rules, should follow these three rules. Then it's called as a type 2 grammar. So this is what you should remember finally, the rules for the production rule basically. Okay, and applications in compiler design. So let us consider a very simple example of a parser for balanced parentheses. You might have done this with stack in your data structures or algorithms. Push parentheses to check if the parentheses are balanced in stack. Okay, now we'll define a very simple grammar that will not accept any other terminal symbols. It will have only this the open bracket and close bracket as terminals. This is non-terminal, set of non-terminals or variables. Okay, and this is a set of terminals. This is a set of production rules, and this is your starting symbol. This is a set of production rules, and this is your starting symbol. Now let us consider the production rule P has this production rule. Okay, now for simplicity, we're not considering any other symbols. We consider only the brackets. Okay, now B and B concatenated together. This is concatenation. Am I right? So in case this B has, it's already balanced. So this B has this, followed by B. So this is B. Okay, so this followed by this. Again, the parentheses are balanced. Why did I say I should substitute? So in the place of B, let us start with B. It can be substituted with B or a B. So in place of this B, again, I can substitute what? Okay, so in place of B, I'll end with a non-terminal epsilon. Okay, fine. So this is acceptable. So when it will be just this bracket. When I substitute epsilon in place of B, it will be this bracket alone. So acceptable. For simplicity, we have not considered any other input symbols like A, B, etc. So that we consider only brackets. Okay, so any sort of strings like this, okay, or any number of open or close bracket, it will be balanced using this production rule. Okay, it accepts a string that has only brackets, okay, no other input symbols, no other terminals, only brackets, open bracket or a closed bracket. So using this production rule, if we expand, it will accept all strings possible. Okay, this is an acceptable string, this is an acceptable string, this is an acceptable string. So the production rules for this is, so what is the purpose of this? Your parse tree that you generate will be matched by the parse tree that the compiler has for your expression. Imagine like I allow other terminal symbols like A and B also. Okay, I have different production rules for allowing A and B. So the whole set of production rules forms the grammar. And when you give an expression as an input, the compiler will generate a parse tree for your expression, and it will have another parse tree with the generic symbols allowed with it. Okay, it will compare both the parse trees and it will decide if your expression is acceptable or not. Okay, so this is one example application, one application of parse trees. The second application, parse trees are these grammars, context-free grammars. They are extensively used in HTML or XML also, markup languages. Okay, so define the rule. To define the rules, how the markup languages should look like. So we have a HTML over here. This is HTML code, and this is the output of this HTML code. So the output of this HTML code will generate something like this. This is list. This is a list element. Okay, ordered list, OL list, ordered list. This is a list elements. LI will be the elements in the list. Okay, so this is a paragraph tag. Paragraph tag need not have a terminal tag. Okay, remember paragraph tag need not have a terminal tag, and LI tag also will not have. These two will not have terminal tags. Okay, so I have to define my parse tree accordingly so that this is accepted. Okay, so to do that, I have, these are all non-terminals. The character, text, doc, element, list item, list are called these are all the non-terminals. Okay, the terminals are A, capital A to Z, and it goes on, like A to Z and numbers 0 to 9, and any special characters that you allow, all these are defined by this character using RR. Okay, it could be B or B, then C or C, all symbols that you allow in a HTML should be defined by character. So it's a character, a single string of length 1. Text is a sequence of characters. Okay, text is a sequence of characters. Again, text does not have any tags. Okay, text does not have any tags. It's just a sequence of characters. And document and element are recursive with respect to each other. So document has an element, okay, and element has a document nested. So they are recursive with respect to each other. So document is a sequence of elements, and in the elements you see either a text or a tag. EM is a tag, EM is /EM, enclosed with doc, okay. P tag, no end tag, just followed by a doc. OL, /OL, enclosed. Enclosure is a list. List is a component enclosed. And again, list is a non-terminal. You can expand it or rewrite it with list item or another list. Okay. Now, list item is another terminal. You can go and expand it with a li tag and a doc. Doc again can be expanded with element. Element has a text. So it goes recursive like this. Okay. So this accepts this set of rules, production rules. This is a set of production rules by HTML. So this set of production rule will accept this. Okay, we'll generate a parse tree for this, and a general parse tree will be available for the markup language, and it will try to match both. So if the parse tree generated by your input string is valid, it will be accepted. Okay, so this is how it is applied. The parse tree concept or a context-free grammar application is like the one we saw before in expression validation in programming languages, and in markup languages also it's used. Okay. And this is another example. This is context-free grammar actually, not a GFG. It's a CFG, context-free grammar. And you can use it in document type classification. So this document type identification, this is used in XML document types, DTD, document type definitions. Okay, so this is used extensively in that also. You can explore more on how it's used. It will be the same as HTML. XML is another markup language. So